Okay, welcome back everybody to this second day of this introductory GPU programming course. The schedule today, while we perhaps just let a few more people filter in, is to just have a bit of a recap of yesterday's content, and we can take any questions you may have on that just now. So at about 10 past or quarter past, I'm going to go on with the content, and this morning I'm going to say something about OpenCL, an alternative programming model for GPUs, which is in the open source domain. Hopefully, having got to grips with some of the basic CUDA ideas, this will start to look fairly familiar. So that's probably of interest to people who are doing C programming. OpenACC directives may be of interest to those doing C and C++, but it will certainly should be of interest to anybody wanting to look at Fortran. So there's a series of exercises related to either one of those choices, really, or well, there's no reason why you should not do both sets of exercises, but you may prefer one or the other. The lunch break, again, is scheduled for 1300 GMT, and the after lunch session at 1400 GMT will look at Kokkos, which is a C++ programming model which offers an abstraction of different GPU and CPU devices, actually. And then we will be seeking to finish by about 1600. Okay, are there any questions? Hang on, let's look. Are there any questions arising from yesterday?
I still struggled to see the difference between the managed and the global the memory thing. It wasn't really clear to me in the Fortran work.
Yeah, for the Fortran, I confess I hadn't really thought much about the Fortran picture. But if you're in CUDA Fortran, which is this extension, it's basically being done for you anyway. It is possible in the CUDA Fortran to use the C API to the CUDA host-side API, but whether there's much value in that in CUDA Fortran, possibly not, if it's as simple as doing an assignment.
Okay, thank you.
The managed memory certainly crops up elsewhere, so it's something, an idea you should at least recognize, I think. But it is probably mainly relevant to the C side. Speaking of, perhaps while we, let's have a go at this. While we're thinking of CUDA runtime API, I should mention, if you haven't discovered this already, the true and correct source of documentation for the CUDA runtime API is found at the NVIDIA website. So hopefully you can see this stuff. You can see there's just from this screen here, hopefully you can see there's quite a lot of it. Certainly don't want to go into all of it. So for example, here in 5.9 memory management, you'll see there is a description of all these API calls. So hopefully we should recognize things like CUDA free. Perhaps one thing it's worth noting here, you'll note all these routines have this what's formerly known as this execution space qualifier in front of them. We saw this double underscore global double underscore yesterday, which is indicating you want this function to be a kernel which is launched from the host onto the device. There are also these other execution space qualifiers, double underscore host double underscore. This indicates that the function should be called from the host. Others are, see here, CUDA free actually is declared host device. This means it can be called either from the host or from the device. So you could call CUDA free from within a kernel, should you so wish. There may be some, I don't know if there are some routines, I don't know if there are any here, are solely device. So that means they may only be called from device code. So that, if you want to write a structured program in which you call functions from a kernel, they should be declared with this device double underscore device double underscore execution space qualifier. You'll also notice all the CUDA API calls have this return this CUDA error type entity, and this can be used to check for errors. Many CUDA programs actually use a macro to automatically check the return types. So you'll see, often see this thing examined for each call in terms by using some macro. I think in the example programs we give, there's an extra helper function to examine the return type. So the other thing to note about errors, if a call is executed asynchronously, errors may also occur asynchronously, which can be slightly confusing at start. So a routine may return immediately and not give an error, but that doesn't mean an error won't occur as the function or kernel or whatever executes asynchronously. So that's just one thing to watch out for there. Okay, there seems to be, I think most people have now returned, so we'll go on to, if there are no more questions, we'll go on to have a look at this issue of Open Compute Language. Okay, as I say, this is an alternative programming model which will be of interest to specifically C programmers. I don't know of any effective Fortran implementation which allows you to use OpenCL, although I confess I haven't looked for a while. But again, hopefully this will be useful as a background. So I'll have a little bit of a look at the background, some of the OpenCL terminology. So while the jargon of OpenCL is different, the basic ideas look rather similar to CUDA. So I hope this will be clear. So if one wants to go about programming with OpenCL, there's a little bit more infrastructure required than for CUDA, so it's not quite so easy to get a simple program off the ground, but the basic issues about allocating and moving memory, declaring kernels and writing kernels which are launched on the GPU are in spirit the same. And we'll have some comments. So OpenCL is an open standard for parallel programming in a very general context, which is broadly thought of as heterogeneous architectures. So where one has a mixture of perhaps CPUs and GPUs, and this could extend to things like FPGAs, field programmable gate arrays, if you've heard of those, and other types of hardware as well. It was originally developed by Apple, and that may be a clue that it's a very important concern in things like mobile phone applications. The standard itself is maintained by an independent group called the Khronos Group, and you can most of the material related to OpenCL and other related topics can be found by following that link there. The standard is supported by most of the relevant manufacturers, including NVIDIA, should be said. So an OpenCL program will run on an NVIDIA GPU. Whether it will run effectively is another question, and whether NVIDIA put a great deal of effort into their OpenCL implementation is a different question. So that's the main link there. Any questions? Okay, so what is it?
I was wondering how it might work on the new Apple chips. I suspect since Apple aren't really supporting OpenCL much anymore, it will be a bit half-hearted.
Yeah. Pass. I don't know the answer to that. So what does OpenCL consist of? There is a language, a kernel language based on ANSIC, which allows you to write your kernels, and there is a host-side API for management of device memory, kernels, and so on. So historically, the kernel functions in OpenCL have often been compiled at runtime. So this is slightly different model from the NVICC compiler, where you compile your source code into an executable in a separate stage, and then you just run the executable. The kernel is actually compiled as part of the runtime procedure, which is a little strange coming from the scientific application domain, but that's you'll see how that works if you look at the example. So the idea behind this is to try and maximize portability. So if you don't know in advance exactly what device your code is going to be run on, you want to compile it on the host at the last possible moment to try and ensure portability. Okay, so in thinking about how one goes about decomposing a problem to run on a GPU, which we assume is made up of many cores, the problem may be split up in a one-dimensional, two-dimensional, or three-dimensional fashion, and the smallest unit of work in the OpenCL jargon is a work item, and work items are grouped into work groups. So hopefully this should be looking rather familiar, where the work items are the analog of threads and the work groups are the analog of the blocks in CUDA. So for example, if your whole problem size had some global dimension in the OpenCL jargon, each block would execute something with local dimension, in that picture 4x4. So how does a kernel look if this is a plain piece of C code where we've defined this function add vectors, which again is this element-wise addition of A and B to give a result C, and we have n elements of the vector. The name of the game is to try, again, the iterations of that loop are independent, so we may hope to parallelize that loop and distribute the iterations between threads. And an OpenCL kernel would look something like this. So here, instead of, whereas in CUDA we had this double underscore global double underscore void function name to specify the execution space, the OpenCL analog is this double underscore kernel with no trailing underscore, you'll note. The other slightly different thing you'll notice for the dummy arguments of this function, these pointers A, B, and C have been declared with this double underscore global memory space qualifier, which there's not really an analog of in CUDA, but these are basically declaring that this memory is in GPU global memory, or GPU. This is a device pointer, if you like. Okay, so again, the loop has disappeared as we saw in CUDA, and we have a mechanism to allow us to identify which work item we're dealing with in the OpenCL jargon, and this is this function get global ID, which is doing the job of thread index in the special variable thread index in the CUDA context. So the argument is the dimension. So the first dimension in C counting is 0. So that's the global ID in a dimension, in the first dimension for this one-dimensional problem. So that's the basic idea. That looks, apart from the details are different, but in spirit that is the same as one we've seen in CUDA. Again, work items in the same work group, one expects to be scheduled on the same unit of computation, e.g. on the same streaming multiprocessor on an NVIDIA card. And as we discussed in the shared memory section yesterday, synchronization is possible between different work items in the same work group or between different threads in the same block, but it's more trouble if you want to do additional synchronization between work groups. And again, items in the same work group can share the same shared memory or local memory, I think, in this OpenCL jargon. So that all looks rather similar. Where things do look more significantly different, perhaps, is on the host side. And it can look a little daunting at first, but there are a certain basic number of steps to be gone through. So first, an OpenCL program should include the standard header cl/opencl.h, and that will give you access to the API. The host side, in order to get something off the ground, then needs to go through a series of steps, which typically involve identifying what is called the platform that you are running on, whether you are a GPU or a CPU, and what identification of what devices are available to the platform, be they either CPU or GPU again. In order then to do something, you create what's called a context, for example, for execution on the device, and you create a queue into which you are going to inject commands, and that is the model for executing code on the target device. You then compile up your read and compile your kernel, and queue the kernel for execution on the device. So perhaps we'll just talk through some of these stages. When we get to the examples, the template example we give you has done a lot of this stuff for you. So perhaps the easiest way is to, if you're interested, is to go and look at what that is doing and try to understand the details. But here's an overview. So the analog of allocating device memory, whereas in CUDA we were able to declare a standard C pointer and allocate device memory to be associated with that pointer. In OpenCL it's slightly different. All device memory references are handled by this opaque entity, which we see at the top here, CL_mem. So this is just a handle to device memory, which we can make an allocation against using this API called CL create buffer. Okay, so all the OpenCL stuff tends to be start with this lowercase CL and then the name of the routine. So the arguments here are this OpenCL context, which I assume we have created in some previous step, which I haven't shown you here. And then there's some values, the first of which is a special value, this CL mem read write, which is saying this memory is both going to be read from and written to, and size in bytes, and another couple of arguments which we don't need to think about here, and the corresponding call to free memory associated with this handle device memory is this CL release mem object. So everything is going through these opaque handles declared as CL mem. So the typical analog of CUDA mem copy, if you want to move data between host and device, these are the appropriate API calls. So CL enqueue write buffer, the first argument of which is this CL queue, which again is an OpenCL Q object, which again I have assumed to have created in the previous step. The buffer is the device memory reference. The CL true at the third argument is a flag to announce that this is a blocking operation, so this will not return until that write has indeed been done. So this is the analog of a sort of synchronous transfer, if you like. The next three, there is an offset from the base pointer, a size in bytes, and the host memory reference is there. The memory you're copying from. And the last three arguments here are to do with events, which I don't really want to discuss today. If you don't care about these, you can just effectively leave them out by this 0, null, null. So that's the sort of that. So the top one there, CL and Q write buffer, is your sort of equivalent of CUDA memcopy host to device, and the analog of device to host is just this CL and Q read buffer, which is coming back the other way. So if the other important step we need to think about is executing a kernel. So this is the sort of analog of this execution configuration. So I've mentioned before that there is a step in which you have to create this compile and create this kernel object, which again I assume I have created in a previous step and is referred to here as this CL kernel handle. So one of the things that traditionally has occurred in OpenCL is the necessity to actually declare what the kernel arguments are at runtime. So if we imagine we had a kernel which is up in this comment at the top, which is void add vectors, which takes a first argument, which is a pointer to float, and a second argument, which is just an integer, we would declare via this CL set kernel arg that this kernel takes a first argument, that is argument 0, the size of which is something like the size of one of these memory references, CL mem, and then the last argument there is the address of that reference. Second argument again to this kernel, so argument position 1 is size of int, and that perhaps for consistency should be address of n if n is the appropriate variable in that that call. So the equivalent of this execution configuration in CUDA is this CL and Q ND for n-dimensional range kernel. which takes as its arguments this CL Q object, the CL kernel object. There's the third argument, ndim, is the number of dimensions in your problem space. Fourth argument, I think, is an offset, which is for the starting position of the in the problem space, which can be 0 or null. The global size is an array, which is the sort of Cartesian size of your problem, and the local size is this work group size. So these are three vectors. Both this global size and local size are potentially three vectors of integers describing the problem space and the local size. Again, these last three arguments, which are 0, null, null, are related to events and event handling, which I'm not going to go into here. And again, you need to think this is an asynchronous operation. So in order to be sure we've finished all our work, we need to check with this CL finish call, the argument of which is actually the queue into which the work has gone. And that will ensure when that returns, we know that we're safe to get the results back. Okay, so I think this is largely a recap of what I've just said. So the OpenCL kernels you often see written in a separate file with a .cl extension. So your host code and your kernels is typically in separate files in traditional OpenCL picture. And that is, so that's a sort of sketch of the process. So that's just a recap on these memory space qualifiers. So the _global is basically the device global memory. There is an analog of the constant memory we talked about yesterday, and there is an analog of the shared memory in the device we talked about yesterday. So all this slightly more complex infrastructure that's required to get a basic program off the ground is there for a purpose, and OpenCL is supposed to be a very general and very flexible framework for heterogeneous architectures, and is supposed to be portable, whereas for CUDA, obviously you are limited to running on NVIDIA devices. So if you really want to go down the OpenCL route, you may want to invest in some infrastructure in code to help you deal with some of this sort of boilerplate stuff that is going on to perform these operations. I should say in passing that there are analogues to most of this stuff in CUDA, looking in the opposite direction, if you like. We just didn't really discuss them yesterday, and for a simple program, you don't need them. So it's a little more simple in CUDA to get a basic program off the ground. I have seen in the past people have tried to produce Fortran interfaces to OpenCL, but I'm not ever been convinced that they were real attempts with a long-term future. So the other thing, and Rupert probably knows more about this than I do, there is quite a lot of activity in the sort of C++ standards area in relation to things like SYCL.
That's right.
Sorry?
Yeah, you're entirely right. There's a lot of overlap between the people who are standardizing SYCL, and a lot of those people are involved in the C++ standardization process.
So yeah, so there is activity, and if anyone's come across Intel 1 API, again, this is a development that is built on top of some of this stuff.
Yeah, so one API is SYCL plus some nice libraries.
But I think that's still a bit of a work in progress. So unless you enjoy building your own compilers and such like, that's one for the future, I think.
The SYCL compilers are on Cirrus, if you want to have a go.
Oh, good. Oh, good. Thanks.
It's a bit experimental.
So Matt, perhaps that's one for Thursday. Perhaps. Okay. So as a matter of interest, is anybody interested in having a go at the OpenCL exercises? By show of hands. Yeah, okay. So there's a special, there's a story behind this. So as I threatened yesterday, at about 25 to 10 this morning, the fire alarm went off in the building where I work. So I had to evacuate, and I was going to put up some instructions to how to use the module you need for OpenCL. So I'll have to, if you want to do the OpenCL exercises, you need a special command which I need to give you. So that's just a warning on that. Okay, any further questions? Okay, I think so that probably took a bit longer than I expected. So what I think I'm going to suggest is that we have now a break until 10 past 11, when I will give the next lecture on OpenACC directives. Anybody going to complain if I say that? And we'll then, when we're done the OpenACC directives, people can go off and have a go at the exercise of their choice, be it OpenCL or directives. Okay, so just a bit of a break until 10 past.